Сейчас, секундочку. So, hi everyone, welcome to our workshop on Introduction to Analytics and Machine Learning with Oracle expert from Europe. Please welcome Jeroen Kloosterman, Product Strategy Director of Analytics and Data Science Department, probably at Oracle. Thank you, Jeroen, for taking the time to share this knowledge with us today. We have a group of girls who will be launching a nano satellite, very exciting thing that we're looking forward. And we already have had one very basic workshop on artificial intelligence, very, very basic. So we're happy to learn from you today. Over to you. Thank you.
Yeah, thank you very much, Elena. Okay, so to make it even more complicated, I've got a cold as well between all the translation, but I hope you understand me. And if at any point I have to repeat something or you have any questions, just feel free to interrupt me. Thanks a lot for the invitation. It's not every day that I have the chance to stand in front of a group of young women that is eager to learn and wants to learn about technology, and even less so from Uzbekistan. So I'm honored to have the chance to speak for you. Yeah, so I work for Oracle, and I'm not sure already what the group knows about Oracle, but I think it helps for the understanding just to give a little bit about what my role is and the company, so it makes more sense now and it lands better. So yeah, Oracle is basically a technology provider, right? So we provide products with which you can basically build anything, software products, right? So we were famous for the database, but nowadays many other things. And maybe easiest for you to understand, you've heard about Amazon Web Services, right? About Google Cloud and Microsoft Cloud or Azure. Well, similar to that, Oracle also has a portfolio in the cloud, which you can build basically anything, any application, but you can also analyze any data that you have. You can do very advanced and exciting things with that. And that's, of course, why we're here. So that's why the title of the session, Introduction to Analytics and Machine Learning, to see what we can do with the data that you're doing with this very nice project of yours of these satellites, right? So I mean, these satellites, they go up in the air, you're collecting all this kind of sensor data. So the question, of course, is what are you going to do with that, right? Are you, okay, so all this data comes in, what is the value of it? Do you have like an objective that's commercial, or maybe you can improve the world somehow, right? You can do something like this. It could be anything, right? And people have different objectives with data, but they use analytics and machine learning as techniques to get value from it, or to get insights from the data. That's why we're here. So I actually I like these kind of thing quite a lot. Trainings. I train quite a lot of my Oracle colleagues in the commercial department, so the people that are selling software and services, and I teach them how to talk about them. But what I actually most like, and what's maybe most similar to this session, is to go to groups of customers and then to explain products to them in kind of a fun way. So recently, excuse me, we've built a number of workshops or trainings really for customers around analytics and machine learning around sports. So everybody knows Formula One, everybody knows well, sailing, maybe not, but we did something about sailing, but also football. So we have like workshops around analytics and machine learning that I've developed and that I bring to customers. And I also want to demonstrate some little pieces of there, because there are some links to what you might be doing with satellite data. So that teaches, so you know a little bit more about Oracle and myself. What are we going to do today? So I've got some customer examples. What do our customers do with our products? I have a little bit of theory about especially the machine learning part. So I'm not sure exactly what you did in the AI workshop, Elena. But the point is the analytics, with which I mean more like visualization and showing your data. I always find that it's kind of self-explanatory once people see it. So we'll see that in a little bit later. Machine learning requires a little bit more theory. So I want to spend a bit of time on that as well. And then a demonstration. So I just want you to see some things in action in a sports context, but I'll link it to the satellite case that you have. So yeah, any questions you have, guys, or any unclarity, just stop me, okay? It's no problem. Well, yeah, before I go into this, you see this interesting painting. I'm not sure if you think it's beautiful or very ugly. That's up to you to decide. But there's one thing very special about it. So it was sold for £400,000, I think, at the Christie's auction. So somebody liked it. But there's something special about this painting, and I'd like you to think about what that special thing is. And then at the very end of the session, we'll come back to it and we'll see how many people get it right. So let's see, okay? And now I have a little poll for you guys. So I'd like to hear a little bit from you first. Let me see if I can start this thing. Okay, let me just move some windows around here. And now I just need to, just a second. You're seeing this, yes, I think? Okay, fantastic. So could you please join me here at this URL? So vvox.app, everybody, and then type in this this number. Okay, you can then all join, and then that gives us a chance to get some input from you guys. So I'd really, because we're going to talk a bit more about machine learning, okay? So I'd really like to know what comes to your mind when you think about machine learning, or even artificial intelligence. What is in the top of your mind? So let's see what you guys think about that. Programming, AI. Okay. Algorithms. Big data. Okay, that's a good one. See what's coming in. Robots. Okay, yeah. Mathematics. Yeah, also a good one. Patterns. Fantastic, guys. Your satellites, of course. Yes. Python, self-driving cars. Awesome. IoT, I see. I'm sure if I'm missing one. Hi, that's also a nice one. Okay. Guys, keep it going. Yeah, so what this tells me is that you're already a pretty well-informed group. So that might have to do with the session that you've already had. I've done this kind of presentation before for other groups. And usually the first thing I see there is Terminator or Skynet or iRobot or this kind of thing. But there's none of that. That's interesting. So you're all mentioning things that are very, very relevant and related. So Python, satellites, algorithms. Okay, so that teaches me a little bit about what you think about this. All these topics are relevant, guys. So very good job. Physics. Okay, that's okay. I have to think about that one. How that's, yeah, I'm sure there are links. C++ algorithms. Oh, guys, you're very advanced, huh? Okay. And cybersecurity. Yeah, you're all on the right track. So all of these topics are somehow related to machine learning. So really good job, I would say. And I'll come back to a whole bunch of these things during the rest of the presentation. NLP, natural language processing. Well, we're going really advanced here. So, oh, this is updating so fast I can't follow it. Neural networks. Yeah, I'm going to have a bit of a chat about that as well. So, and decision making. Very good point. Decision making is what it's all about, right? So getting values and insights from data. I'm going to stop this for now, but thanks a lot. And it already tells me a little bit about the group. So that's really good to see. Thanks a lot, guys. You can keep putting it in. I'll keep it here in the background. I'll go back to the presentation. Okay. Just a second. Yeah, my Uzbek is not that strong right now, but okay, we'll ignore that one. Okay. Okay, guys. So let's talk a little bit about this machine learning, right? And I'll talk a little bit about some basics there. So I think it's easier if you compare it to classical programming. Okay, so in the end, when we program something, we want the computer to do something, right? Usually also with some data that goes into it. We want it to get an answer for us, or we want it to take some kind of action, right? Now let's take a simple example. So imagine you have a piece of data, a temperature in Fahrenheit, and you want to know what is the temperature actually in Celsius. Now that's a very simple problem for a programmer or for a computer. They can simply take that piece of data. They have their own rules or their program, and out of it comes the temperature in Celsius. That's easy, right? And why can the programmer do that? Because he knows exactly what the relationship is between what goes in and what must come out, right? This, the Fahrenheit and the Celsius. There's a formula for it. He knows that. That's the reason we can do that, and that's how we've been programming things forever, right? Since computers exist. So sometimes problems are not that clear and they're not so well defined. So imagine now the question is, yeah, we still want to know as an output what is a temperature in Celsius, but we don't have temperature in Fahrenheit. Instead, we have humidity, we've got altitude, we've got wind speed. I'm just trying to put it a bit in context of your satellites, right? But imagine you have these kind of measurements. And then we ask a programmer, okay, can you please write a little program for that? And he will tell you, dude, I have no idea. How do I go from that to the temperature, right? That's not possible. So that's where machine learning can come in. And that takes a very, very different approach to this problem, because obviously we don't have a clear rule how to go from those inputs to the output. That's not obvious to us. But what we may have actually is a lot of data from the past, for example, from historical readings on, okay, we have an altitude, we have humidity, we have wind speed, or whatever, the time of the day. I don't know what would be relevant for this, but imagine. And we also have the right answer already for that. What was the temperature at that point in time, right? So we've got the data and the answers already. From that, you can use algorithms, you can use machine learning algorithms to actually find the patterns in the data and to come up with the rules. So the output is actually the rules, if that makes sense. And in fact, rules is just a weird way of saying a model, okay? Because what we're creating is a model of the data that really captures the patterns in the data. And once you have that, then you can go to town with it and you can predict any temperature in this case. Okay, so it could be, and this could be many other problems. This principle is applicable to many situations. Okay, and we're going to look at a few examples. Elaine, is all okay, or should my speed is okay, or yeah, we're going well. Fantastic. Guys, if you have any questions, feel free to post them, and otherwise I'll just keep on going at this speed. Okay. All right. So I just want to show you a few examples of what some of our customers are doing with data, with analytics, with machine learning in this area. And there's this company or this customer of ours called AgroScout. So what they do is that their customers are farmers, okay, farmers that do agriculture. And the farmers have very big fields where all kinds of things grows, right? The wheat, corn, you name it, right? Any kind of food products can grow there. So they send these drones out above the fields, and they look at the fields. So they have a camera on board, and they can see from above, hey, that part of the field is maybe a little bit dry, or that part of the field is actually being attacked by insects or by bugs. So the great thing about this solution is that the farmer can then see, hey, there's something wrong there. So he can take action before it goes worse, right? So he can give some water to the field, or he can put pesticides on only that part of the field. He doesn't have to do the whole field, which of course is kind of an environmental disaster. So that's very good for the world. It's good for food production, and it's a good thing, right? Now, what is the link with the machine learning here? The link is that you have these cameras on board. The images from those cameras, it's not human beings looking at them. Okay, that would be impractical. It's like they fly around all day. And also, the human eye is actually not that good at spotting the problems. Okay, it's not. It can look at a picture, but it could be, oh, it's good, or maybe it's not good, right? So what they've done instead is they've used machine learning for this, and they've taken loads of pictures from fields from the past, and also let's say the readings from down on the field. Was there actually an insect? Was it actually dry, right? And with that, just like in the previous example, you can train a machine learning model to find the patterns, not in like structured data like I talked about earlier, but in image data, right? And that's the interesting thing about it. So this machine learning allows this to be an automated process. You don't need a human being, and it can do it a lot better than the human being could in the first place. So that's all really positive stuff, right? I don't know if your satellite has image technology, or maybe it doesn't, but you could in a future, or V2, right? But this kind of thing starts to come close to that. So another example, guys. So this is called the National Institute for Health Research. That's also a customer of ours. And they work with what are called cochlear implants. So that is for people that can't hear so well. They get devices on their ears, but they're not like the traditional implants. Devices. They actually go into, it's like surgery. No, it's going into the head. And the interesting thing about these implants, I didn't know this actually until a year ago, but some people that were completely deaf can sometimes even hear with this again. So, and it works for young children, and it works for adults. So it's really quite amazing technology. What is the challenge though with this thing? That you have to imagine that these cochlear implants, they've got a whole bunch of electrodes that kind of, take the sound, and they transfer it to the hearing nerve directly. And these electrodes, these 20 of them, they all need to be tuned. Okay, so they have to be like at a different volume or frequency. I'm not sure what it is, but they need a certain setting. Okay, and they also need a setting that makes sense between the settings of all the electrodes, because if you don't tune it correctly, it's not comfortable for the wearer, or it's not comfortable for the patient. Or patient, maybe that's not the right word, but the person wearing it, and it's just not comfortable, or they don't hear well. And to train these or to tune those electrodes, they actually have to go to an expert. They need to try out many different settings. They say, is it okay like this? Is it not? And then over time, it starts to get a bit better. And normally they have to go in like 6-7 times, maybe in a year, just for that tuning, right? So it's very impractical, very time consuming. So also here, this NIHR, they wanted to look at machine learning to see how can we do that better. And they looked at loads of tuning settings, historical tuning settings, and let's say feedback from patients on how well it worked, etc. And from that, they were able to train models that now allow them actually to make the right settings for each individual, which are different all the time, much faster and much more automatic. So maybe now the patient has to come in, they set it once and he comes back maybe one other time and it's done, right? So I think very good news for the world that this kind of thing is possible, okay? Right, now something completely different. And this is more again on structured data. So, I mean, with structured data, I mean things that fit in an Excel spreadsheet, for example, right? Or like very distinct numbers. So the NHS, the National Health Service of Great Britain, of the United Kingdom, they're the National Health Service, and they've also been looking at machine learning to do things better. So they wanted to look at using it for finding weird things or finding the odd cases. So they looked, for example, at dentists. So the way it works is that the patient goes to the dentist gives him some kind of treatment, and then the NHS, they get their money. Also, the dentists get their money from the NHS, right? So they do like a claim for the money. So they used machine learning for let's say anomaly detection, finding the anomalies in the data. And with that, they were able to see, hey, that dentist is doing many treatments, or those dentists are doing treatments that don't seem to make sense, or that don't fit in the normal pattern of what a dentist would be doing. And it allowed them actually to find a whole bunch of dentists that were not playing fair, right? And that were trying to claim money that they shouldn't be doing. And of course, that's all money that can be spent much better on the actual healthcare of other patients. So yeah, so also good machine learning to find the odd one out and to save money for an institution that really needs it for other things. Okay. Any questions, guys, at this point? Those were just some examples.
We do have question in the chat. It's not while it's not connected with the examples. It's just very deep question. Like for me, like Sarvina is asking, does machine learning fall into some of programming paradigms, or has some sort of connection with any of the programming paradigms? So let's.
Let me see how I interpret that. Does it? Yeah, I mean, the connection is that you always try to let the computer do something in the end. No, that's the connection. But the way you reach that goal is very different. So instead of putting all the rules, the lines in of how you achieve that objective yourself as the human being, you let basically an algorithm find out from data how to get there. So that's the difference. In the end, machine learning is still a bit of programming as well, but here the programming is, hey, this is the data that comes in, find the patterns in it and apply it to that new data. So it's still programming in that sense, but it's much more data centric. Okay, so yeah, I mean, in the end, to do machine learning, almost always you do it in Python, or you do it in even SQL, or in Java or whatever. But the emphasis is much more on getting the data ready, identifying the right data. Okay, so that's the how they compare, I think.
Thank you.
Okay.
And another question about National Health Service and how they collected data about drug prescriptions.
Yeah, that's basically their business, or that's their whole model, right? So all those doctors that are connected to it, all that data is theirs. So all the things that the doctors do, and all the money that goes around and goes to the doctor, that's all theirs. And they actually already had this data for a very long time. They were sitting on that, right? They've been in existence for, I don't know how many decades, for hundreds of years, I don't know. But they started to look at the data in a different way. Okay, so it wasn't a matter of getting the data for them. That wasn't the issue. They just had this idea, let's do something different with it. Okay. What are the key requirements? I'm reading it myself now, Elena, sorry. Apologies. You can be the moderator. What are the key requirements for becoming a data analyst? Yeah, okay, that's a good one. Okay, I'm just thinking about that one. You need a bit of statistical background. You need some technical background. I think most important, or let's see the thing that maybe people expect a little bit less. Okay, let's just focus on that. So you need the obvious things, right? You need like a bit of the technical knowledge and the statistical skills. Everybody gets that. But I think where a lot of people kind of struggle, even if they get a job in this area, is that you need to know about the particular business or the context where you want to apply your analytical skills. So if you are in a commercial situation, you need to know all about sales and how the situation works with your customers and what kind of customers there are, to be able also to choose the right analysis, right? And to choose the right method. So it's not just technical knowledge, it's also a bit of business knowledge or knowing the area where you're going to apply it. So I hope that's a good answer for you. Okay, I'll let you moderate, Elena, and you decide which questions we do now or later.
Yeah, maybe we can ask, take one question regarding the example that you shared, and then take the other at the end. So I translated question from Zebahon. It was in Uzbek, and you also can see it. It's about teaching robot to diagnose with software. It's like in the chat.
Can you repeat that? So I didn't get it.
It's whether is it possible to teach robots to diagnose using software, for example, to make an accurate diagnosis in medicine according to the symptoms and results of the analysis.
Yeah, in fact, that case exists. So it's the same principle, right? So if you the same cases that we talked with the Agro Scout. So in the end, like an MRI scan, right? If you go into the big machine and they take an image of that with all its calls and everything. If you have loads of example data from the past where you have those MRI scans and annotated as well a version of that the doctor said, hey, there's something wrong, right? Or that's something that needs investigation. That's again training data where machine learning model can be built on, and that's being applied in several medical situations already, that kind of case. And the interesting thing is that you can have you can train that on data from many doctors, right? So normally it's all in the head of one doctor, and he needs to look at like an MRI scan, and from his knowledge, you depend on that knowledge. But if you train a model, in principle, you could have the combined strength of 1,000 doctors, right? So that's kind of one of the attractive things, apart from being able to have a lot higher workload, right? The machine never gets tired. A machine can handle as much as you want, right? So that's all very positive. Yeah.
Thank you. So yeah, we can answer other questions at the end, if it's okay.
Good. Yeah, okay. I'm also looking a bit at time. Yeah, so we're half an hour in, so that's good. All right, guys. So let's continue here. And then a little bit about the context. So you talked already about AI, so I'm not sure how much, maybe I'll go through this a bit faster. So the terminology, right? What is AI? What is machine learning? What is deep learning, etc. I'm always a little bit careful with using the term AI. And why is that? Because it's not really only about what is possible today, but it also has this expectation in it of what people think is going to be possible, right? So the idea that you can have like one single piece of software or one kind of thing that you've built that can handle any task, right? Like, I don't know, clean the house for me, do my tax declaration or whatever, and that needs to be able to do all those things. That doesn't exist. Okay, so there is no Skynet or Terminator yet, at least not now. But what does exist is machine learning algorithms and models that are all good at doing one particular thing. Okay, so we looked at those examples. No, so if you have a picture of a field of crop and you ask to one model, find out what's going on here, what are the problems here, and where are those problems, right? That's a very particular model. If you have, let me see, what do we have? The hearing implant. No, so here's a patient with a hearing implant. Find me the best settings for the 20 electrodes. A very specific thing. Or here's a set of dentists and all the data around those dentists. Find me the one that's weird, right? That's the odd one out. A very particular thing that model can do. So that's basically how things work nowadays. We train models for very specific tasks. Some data goes in and a decision comes out, right? That's what machine learning is. It's not this general thing that can say, okay, paint my house and also go to the supermarket. You know, that's it. It's not so generalized. So if you can identify many small things in a business or in any kind of situation, many of those A to B mappings that you couldn't solve with programming, but that you do have data about them and measurements, you may be able to attack the problem with machine learning. Okay, now deep learning, what is that? That is basically a subset of that, or further specialization. It's also machine learning. What is the difference here? This uses always neural networks, or even deep neural networks. And the idea is that these algorithms or these models are modeled kind of like how a biological brain works. So let's say the classical machine learning are more like mathematical models, okay? And deep learning, that is more like a whole combination of neurons, just like they are in the human brain or an animal brain, okay? So how that works. And or maybe put this a little bit in the context of the satellites. So the classical machine learning, that's like taking those structured data points, sensor readings, right? The temperature, the humidity, whatever, making a prediction on that or finding the pattern in those kind of data. And deep learning, that is also able to work with very different kinds of data. So not necessarily with just those structured data things, but also things with images, with audio, with video. And that's where there's been a lot of development actually in the last few years. Yeah, which has given machine learning, I think in general, such a big push in the last 5 or 7 years. The deep learning part has developed a lot, but also for machine learning, there's, well, let's say the classical machine learning, there's many business cases. And what I see around me is that deep learning, that's what interests a lot of people. And they say, wow, is that all possible now? But it's sort of created this renewed interest in the classical machine learning things, and all companies and everybody now sees the benefits of that and want to use it. Okay, so it's all good, I think. Okay, and data science, that's just basically the field. That's the study of all of these technologies and bringing it together to reach a sort of business goal or a goal that you have. It's also about how do you do the data preparation and how do you take such a model and actually get value out of it. Okay, so that's that. If you want to pop in another question, Elena, you just tell me, and otherwise I go on. Okay. So a little bit more about this theory then. How does that work? And we're going to this kind of classical machine learning. So imagine that you want to predict what humidity is based on temperature. Now, I'm not sure the example makes a lot of sense, but let's say you want to do that, right? Or fill in any kind of metrics that you have in your mind. How do we do that? Well, machine learning is not about putting the rule in yourself. Machine learning is finding out what the relationships are from example data, right? So we have the data. How do you then build a model from that? Well, you start by plotting the data. Okay, so here I kind of already, even as a human being, the relationship between the two is kind of there. I can see it. Oh, I see on the horizontal axis my temperature. And I see as that gets higher, the humidity goes down, right? So the humidity here is the output, is the thing I'd like to predict. And the input variable or the feature, that's the temperature, no? That is what goes in. So how do I create a model out of that? Well, kind of simply put, it's about drawing a line through these points that fits as well as possible. Kind of like this, okay? So in fact, that is what the linear regression algorithm does, right? It tries to fit a line that fits your example data as well as possible, okay? So yeah, this looks pretty good to me. Because you can imagine that the points could be organized differently. And then, I'm not sure if you see this on camera. So you have this certain angle of the line. The angle could be like this or even going up. And it could also have a different height, right? So let's say the intercept here, if I can go to my screen here, the intercept could be in a different place. Right now it's like 0.95. It could be much lower, for example, right? So training a model is basically about fitting a line to example data. Very, very simple put, okay? And if you have done that, you've trained your model, we say, and then you can say for the future cases, okay, now I've got a temperature. I've got a temperature of 16.5 or 17. Tell me what the humidity would be, my dear model. And the model will tell you, okay, it will be about 0.55. And that's what we call inference, or we call prediction, okay? So, so that's the basic idea. Let me move on a bit quicker, maybe. Okay, so how does it fit this line? How does this training work? Well, you see this red line here, right? So what is this red line? It's the difference between what the model says that the humidity should be and what the actual humidity is according to my training data. And you want to have that as small as possible for all of your data points. So we kind of add all these distances together, and that tells us the cost of the model. It's a little bit different, the formula for it, but the closer the distances of all these points, the better, right? And you want that cost, you want to minimize that cost at all points. So there's a mathematical formula for this line, right? It's what is it? Y is ax plus b. You basically have the angle of the line, you have the intercept, and you try to optimize those two variables as well as possible to have the cost as low as possible. So that's what it's doing. It's kind of moving this line around and to try to get the best fit. So that's very simple. We're doing this with one variable, but in practice, you're going to have usually quite a few more. Well, or two can be, but could also be many more. It could be variables of which you're not even quite sure how much value there is in there to get a prediction. So maybe you also have, I don't know, wind speed is here as well, right? But you're not quite sure if that has an influence at all, but you can try it out, okay? So if you have multiple input variables, it kind of becomes more a multi-dimensional problem about solving. It's not a line, it's more like a, I'm not sure what the English word for that is, but I'm sure you know what I mean. And also here, what is simple is that this is just one single line. Very often it is a curve, right, between a relationship between two variables. So also that is kind of a simplification here, but it is how the linear regression algorithm works. And you've got many other algorithms that do this in a different way, okay? So that can work with curves, and that can work also with many other variables. Okay, let's see. So kind of this process explained very quickly again. You've got a training phase at the top and you've got a prediction phase. So in the training phase, all of my data goes in, all the things that are kind of my input that I use to predict my target, which is the humidity in this case. So the training algorithm tries to find the optimal formula, let's say the settings for all of these constants in the equation, right? To come up with a model that fits as well as possible. Once you have the model, you get to the prediction phase. And then, of course, you don't have the humidity yet, right? You don't have your output yet, but that's what you're trying to determine. So you get all the other data points in. you feed it into your prediction, the model is used then to come up with that number. Basically, it's executing that formula, right, that you created in the model. And well, let's say it's 0.85 that comes out of it. So this very simple idea, learning from data, can be very, very powerful. You can predict house prices. You can predict the likelihood that somebody is going to buy a product. You can predict how many people are going to enter into a shop, or you can predict the chance that the satellite is going to freeze and fall down. I don't know, right? You can many cases that you can't capture in a formula yourself as a human being. It's too complicated. You don't really know, but by feeding enough data, these algorithms can find patterns in there, right? So that's the basics. Okay. So I'll go over this a bit quicker maybe. Yeah, so then a different kind of algorithm. That's the neural network. And I already said it kind of looks like the human brain or a brain, right? If you look at an image, and an image can be an image of a dog or a cat, or it can be a satellite image, or it can be an image of a written digit. That's also an image in the end. If I ask you what is written here, everybody says that's 504,192. So it looks very simple task, but actually it is not an easy task. It's just that humans are living beings, let's just say that, are very good at visual interpretation. Okay, so we've got a visual cortex with all these neurons and things in it. It's in multiple layers, so it can work with like increasing abstraction to make sense what's actually coming in through our eyes. And we kind of have a supercomputer in our heads now. But to really appreciate how complicated this problem really is, again, think about classical programming. How would you solve this problem if you had to write a program for it? How would you recognize the 9 here, right? Would you write a program that can recognize the circle here? What if there's a hole in the circle? What if it's a little bit grayed out, or what it's flattened or whatever? It's actually a very, very complicated problem. You can't do it with programming. So that's actually where neural networks come in. And as I mentioned before, the reason that they're so good at this kind of visual tasks is they have an architecture that's very similar that we also have in our natural life, in how we work with images. And that's quite different from trying to find these single mathematical equations. It's actually, there's a lot more parameters that go into these neural networks, which I'll talk about in, right now actually. So what does a neural network consist of? If you look here on the left-hand side, that's what we call a perceptron, okay? And a perceptron is like the smallest unit possible, of which is all built up. And you can make a very small decision with a perceptron. So imagine I want to decide whether I'm going to the cinema tonight. Then there could be 3 factors that are important for me to go to the cinema. So maybe how nice is the weather, right? Is it raining or not? What do you think about this movie? Is it even a nice movie, right? And do I have enough money in my pocket as well? That could be a factor. And then you have maybe different, let's say, priorities for each of these factors. So maybe I absolutely don't want to leave the house if it's raining. Okay, so that has a very big weight for me. So each of these things gets a weight attached to it. Okay, and then in the perceptron, all of these inputs are multiplied by their weights. They're of relative importance in a way. And if that number reaches a certain threshold, a certain basic value, then, like, let's say the signal moves on and kind of a decision has been made. Okay, and you can imagine that different decisions are made depending on how I set these weights and these thresholds. So the configuration of this one perceptron has all of these, like 4 parameters at least. I think there's more in real life for a neuron or a perceptron. Okay, now in itself, it seems very trivial maybe, but it does show it can make a very simple decision. Now, the idea is that if you put many of these perceptrons in a network like here, and you have different layers, so you go from left to right, from layer 1 to layer 2 to the output layer, you can actually create very subtle decisions. And subtle means very accurate, very taking many things into consideration and really making a good decision, okay? Because like in the first layer, you make maybe a very basic, let's say, a basic interpretation of the input signal. And on the second layer, it can make a higher level, a more abstract decision on that, until you reach like a high quality decision when you get to the output, okay? So that's the idea. So imagine we have a model to recognize digits, okay, handwritten digits. So what happens? For example, I've got this one digit, it looks like a 9, okay? It goes into the network, and each of the pixels of the digit, let's say it's a matrix of 30 by 30, right, is connected to one of the inputs of the neural network. And it goes through the neural network with all of the weights, and some neurons fires, others don't. It goes all the way through. And then out of it in the output layer comes the decision, hey, this is likely a digit 9 or 7, okay? So that's how it works. And the principle is the same as what we saw with the linear regression. So it's also a training phase and a prediction phase. Only the input now is images and also something that tells me, hey, what is that actual image representing? So in this case, in the right bottom, that 9 is indeed a 9, right? So you need to have those labels, of course, to give the right examples. And what happens here during the training is that you've got, if you think about it, in the linear regression, you have two parameters, right? It has the angle of the line, and it had the height of the intercept on the line. Well, here, so, and you have to adapt those, right, in the training. That's what happened there. Here, you do the same, but you have many, many more parameters to train. You have all of those weights and those thresholds in the neural network that need to be optimized. Does it make sense? So what happens in the training algorithm, it does many steps, and it starts with a completely random network, with which I mean maybe the structure of the network is there, so many neurons in so many layers, but the weights are completely random. So if you run the training set through it, out of it comes complete nonsense. Yeah, it will almost never get it right. Well, 1 in 10, okay? But then over time, the training algorithm actually adapts the weights of each of these neurons slowly, so that it's a bit more likely to say the right answer for each of the training examples. And there's a process for that. It's called back propagation. It's mathematically actually quite tricky, but you can consider it a black box, right? We don't have to understand all of the internals either of these things. And out of it comes an optimized model with all of the right weights to fit the training set as best as possible. And again, once you have that, you can come with your example new data, your handwritten digit. Well, is this a 3 or is this a 7? Well, according to the model, it's a 7, right? So that's the basic thing. So yeah, this can be applied to many things. Face recognition, you know it from your phone, speech recognition, self-driving car, the medical images that you mentioned, and satellite images, of course, right? That's also where it can have a fit. So that's it. Yeah, one more thing here. So I found this is not a customer case of Oracle, but the World Bank, they actually use satellite images kind of in this way. Now, this is a satellite image from out of space. I'm not sure how high your satellites go. It goes into the stratosphere, no, or something, I believe. Yeah, okay. But still, the principle of it applies, right? You have an overview of something that's below at a very high altitude. And they want to say what is the poverty in different geographical regions, especially in the developing countries. So they know where to focus their efforts and where to help people, for example. So how did they do that in the past? Well, they would simply go from door to door with the census. They would ask questions to the people with paperwork, right? So that's very painful, very slow, very expensive to do. And once you've got that done, maybe 10 years later, that poverty information is like completely outdated, right? It's useless. So they looked at a solution for that. And they first started to look at using actually night lights. So to see, when it's dark, how many lights are on in each region. And they use that kind of as an indicator to try to understand how much poverty there is. Problem was that was very inaccurate, okay? Because you could have very big zones that are in complete darkness, and it could be a natural area, or it could just be slums, right? Where people can't even afford to put a light on or have no electricity. So that didn't work. And instead, they started to work with imagery from the daytime. So in the daytime, you can see everything, and you can find all kinds of features like the roads that are there. Are the roads paved or are they dirt roads? Or do you have the roofs of the houses? Are they metal or are they, well, I don't know the materials, but you can imagine that you can use features from that, right? And again, here the training phase is the information that they already had. So they've done those censuses in the past, right? So they have the ground truth, as we call it. They could compare those with, or they can feed those into a training algorithm with satellite images. And then these deep neural networks, they're so smart that they can actually discover what are the important features to kind of predict the poverty. So I mentioned whether a road is a dirt road or a paved road, but you don't have to tell a neural network what to look for, right? It will start to learn that by itself. You don't have to say in advance, hey, you need to see what kind of material the roof is made of. It will find those things itself. And if in fact, when a model is built, we don't even know how it does it, right? But it may be able to find all kinds of features in there that a human being can't. And that's the interesting thing about it. So now they've got this model they can just apply to any satellite image. And at any point in time, they can get an estimate of the poverty levels, which is great for the work that they want to do. Okay. So now I've got a demonstration as well ready, but maybe now we take a few more questions. Is that a good idea?
Yeah, thank you for so many examples. We have like 3 questions that are related to the examples also. The first one is, can we increase the accuracy of the model if we have more historical data?
Yeah, generally speaking, it's a good thing to have more example data. Generally speaking, you can get accuracy. So we need many examples to be sure about if it's just a one-off reading, right? Or if you get many kind of examples that confirm those readings of those relationships, you can be much more sure about your decision and create a more accurate reading. But more isn't always better, right? It's not only a matter of quantity, it's also very much a matter of quality data. So if you have like your satellite is having sensor readings that very often are not good, right? So maybe because it hits the wind a little bit differently, your temperature reading is completely different. I'm just imagining something here, right? That can really seriously mess up your model, because it looks like a certain reading is happening, but it's not the right reading. Yeah, so you can sometimes put in more data, but it's more about also the quality of that data. Okay.
Thank you. So, another question is the number of neurons is the same as we have in the human brain?
No, you can design these So what you typically do is that you design the structure of the neural network, okay? But you don't put in the weights. The weights are being trained. And depending on the problem, you can have neural networks of very different dimensions. Yeah, there's also a thing like convolutional neural network, but you have different amounts of layers. You have different, let's say, depth of these layers can have a different amount of neurons in it. And the depth can be very different as well, depending on the problem. Okay, so there are, now talking about the amount of neurons, I don't know what astronomical number of neurons we have in the human brain from my head, but it must be enormous. I know there are some incredibly big models. For example, on internet, there is one model, I think it's GPT-3, excuse me, that it's called. I'm not sure if you ever played with that. It's been in the news that it will actually write a story for you if you start the story. I'm not sure if you heard about that. But that supposedly is made of an enormous amount of let's say, connections and neurons. But I'm not sure how they compare. So.
Yeah, and thank you. And if we can have like one or two more questions. Another one is, when we have a lot of data, what about like overfitting or overlapping of this data? If I got the question right.
Yeah. So sometimes you can do your best so much on your training data that, I don't know, you want to that on the training data, it seems that you're doing an incredibly good job, and you can, by all the input data that goes in, you can produce exactly also what the training said should be the value, right? And you've done really your best on that, and it works really well. But then you come with another set of data that's new, that the model has never seen, and then you actually get a very bad result. Yeah, that can happen. So it can mean different things. It can mean that your initial training set is actually not wide enough. Maybe you didn't have enough data, or you didn't have enough, let's say, broad cases, but you just happen to have a subset of the data where that model works for. It can also mean that the situation has changed, right? So you're predicting something, but there's been a phenomenon, I don't know, like the COVID changed everything, right? And suddenly the whole market works differently, and then your model doesn't work anymore. So that kind of thing can also happen. So these are very important considerations, and we always have to keep checking the accuracy of our models. Also, once we start using them, not just blindly believe that they're right. It's just like with human beings, right? With our neural networks in our brain, we've learned to do something in a certain way, but then things around us change, and we need to adapt. So it's kind of the same with the models that we train.
Thank you. And we can answer other questions like later, probably.
Okay, good. Okay, guys, then I've got a bit of a demonstration also with me. So I hope that that helps, right? This visual aspect. Let me just go and log in again, because this usually is necessary. So this is actually, I wanted to show you some examples from those sports trainings that we do for customers. They're kind of fun to do for them. And I think there's also a few analogies with what you could be doing with your satellite. So for example, here I've got this, is this properly visible, Elena, on the screens? Yeah, you see it? Okay. So here you've got this, this workshop that we did, our training for our customers on sailing data. This is for a sailing competition called SailGP. And you have to imagine you've got these very high-speed boats, catamarans, that go over the water. And while these boats go over the water, we're collecting all kinds of information from them, their position, but all kinds of sensors as well, like the temperature as well, the wind speed, of course, the wind direction, how high they are coming from the water. I think there's like 300 or 500 sensors on these boats. It's really quite incredible. So in that sense, I think it kind of is similar to what you do with satellites, right? You also have this temporal aspect, and you have sensor readings over time. So let's have a look at how such a data set looks. And this is using one of the products in the Oracle Cloud, okay? Called the Analytics Cloud. So let's see when this is loading. Okay, let's see when this comes up. But the idea is that, yeah, okay, each of these lines of these records is one moment in time of 1 second of one of these boats. Okay, so for example, this is the reading of all the sensor values of the Great Britain boat at 50 seconds. Okay, so we have it every second in this case. That's the frequency. And we kind of made it easy for ourselves. So we have all of these sensor readings and all of the columns that come after it. So this is, for example, that tells you how far does it come out of the water. What is the heading, right? What is the angle towards the wind? You can't imagine so many sensors here. I don't even understand all of them. Like what was the boat speed? We have all of that. And maybe that's an interesting thing to know. So very often what you have to do with these sensor values, you have to sync them. Okay, Elena, you were writing something about that in your text already. So to make it easy for ourselves, we've already synced the sensor value. So one sensor maybe comes in twice per second, once comes in once per second. But here we always see the latest value of each of the sensors in at that moment in time. Okay, so that's already done. So sometimes you just want to visualize the data, right? So let's just start to do some basic things, and then we can gradually move on to the machine learning bit. So I'm going to just create a workbook for this. Don't save. Okay. So we're gonna just take the team name. This is B name. Okay, that's the name of the team. And we're gonna see how long they were sailing. So basically how many of those sensor readings we had for each of them. And just dragging that over. And that already creates some charts for me. So I just want to show this to you also to contrast it a little bit with Python. I'm not sure what tools you're going to use. Yeah, Python is often the choice, but this is kind of a very easy way to do a bit of exploration, right? Because sometimes you know exactly what you want to show and you build the chart like with Python, but sometimes you want to be more playful with the data and explore a little bit. So this is where this can help a lot. So in this case, this tells me how long all of the teams have been sailing. So let me just order this by time sailed. So very simply put, Great Britain was the winner because they only had to sail, what was it, 7,000 seconds, and they were done. Okay, so they went over the finish line first. In fact, Japan and USA, I don't think they even finished because they had some kind of accident here. In fact, let me just remove them. Okay, so let's do that. So we just want you to get a feeling, right, for how this works. Japan and USA, we remove those. This was basically the result of the race, right? The first of the 6 teams, how they came in. So now, let's say we want to see something about what speeds did these boats go on. Okay, so I can imagine you want to do something like that with the satellite as well. So again, we take the name and we take the sensor value for the boat speed. So I'm just taking that boat speed in knots, just dragging this over. And in this case, maybe not surprising, it's also the Great Britain team that has the highest maximum boat speed, I have to say. Yeah, this is, and I did that before. This is not the average boat. This is the maximum boat speed that they reached. In Great Britain, reached 51 knots. That's 94 kilometers per hour, I believe. So that's pretty crazy on the water. Not sure how fast your satellite is going to go, but this is the speed for these boats. okay, let's do something else. So sometimes you also need some simple calculation between your sensor values, right? So we've given an example of that. So these boats, they, for example, they can do this phenomenon. Do you see this? How the boat comes out of the water? You see that, right? That happens at very high speed. They have kind of a wing on the water that pushes them out if they go fast enough. And for these boats, that's a very important metric. How much of the time are they out of the water? Okay, so I'm not sure if you got something similar with your satellite, but I can imagine you need to do some calculation. So we're going to do that as well. Where it is here. So I'm going to create a quick calculation here. And this thing is called foiling, okay, this phenomenon. So the amount of time that a boat is out of the water divided by that it was just in the race. Okay, I'm going to say that times 100%. Oh, we'll call it percentage flying time, okay? Like this, save. And now I've got this new metric here that I've just created. And I can again say, okay, take that for all of the 4 boats, 6 boats. And we can see how much each of them was flying. Okay, now, what is another thing that the satellites, well, you don't see it so well. You're right. I see you kind of, indeed, this is not so accurate. So let me first order it from high to low. Maybe this is not the best way to represent this. So we could take it maybe as just a table, right? And we can be a bit more accurate about what this flying time was, right? So now the point is I want to show you that you can play with this, right? That's the idea. So, right. So what is something that these two things also have in common? So the boats and the satellite is that it's all about location as well. Okay. So in this case, do you have a GPS sensor on it, Elena, or not?
Yeah, we will.
Ah, fantastic. Okay, so that's great. So most likely you have some kind of requirement to show where the satellite is. Okay, so these boats also have that. So they've got a latitude, longitude, also coming from sensors. All right. So what we can do is we can take the position of these boats and visualize them. So we can take these latitude, longitude, and I'm going to pick a map visualization for this. Okay. So it looks a bit chaotic. If I scroll out, not sure if anybody recognizes where this is, or Hamilton. Anybody knows where this is? Would be very impressed if you know that. This is Bermuda. Okay, this is Bermuda, and this is where the race takes place. So, okay, that's not the point. So this is a bit chaotic because we see the whole race for all of the teams. All right. So let's say we only want to focus on the start of the race. I don't know, you've your satellite, you've identified a certain amount of time you want to investigate a bit deeper. What happened there, right? So I'm going to take the time group, move it over here. Let's say we want to have the 10 seconds before the start until the 10 seconds just after the start. So I change it to a range. And we say 10 seconds to 10 seconds after. Okay. So that makes a bit more sense already, and we can kind of see what's happening in that moment. I don't know, maybe you want to compare positions of 2 satellites. I don't know what. I'll let you get the inspiration and see how you could, use that or apply that. So now, okay, let's say we want to investigate the speed that they had exactly at the moment of the start, right? So let me just take again the boat speed. and I say, okay, boat speed, move that to the car instead of the team. So you see that? So now this becomes, the car becomes the speed. And now I've lost the context of which is which team. So I can take this B name again, and I will drag it to shape instead of car. So now that's back, right? So now each different shape says something about which team it was. And so this is what I mean, playing with data and quickly getting an idea without having to code anything. Okay, so that can be really, really useful, even just as preparation before you start doing some programming on it, or some actual machine learning in Python or whatever. Okay, so let me then, because I'm looking at the time, quickly do the machine learning bit, which I think is the most interesting. So I've got a data set for Formula One. Okay, and Formula One, we've got many races in Formula One. I think from all the races from 1950 until the end of 2021. Let me see where I've got that, races here. So these races, yes, this is taking a little while, as it seems. So let me already explain a little bit. We've got all kinds of information about each race. Right? We know where it took place, what was the date, but we also know what was the weather during that race. We know, yeah, here you go, right? So it's one record per race in this case. The year, the round, the location. What we also know, I'm skipping this one for a second, is, yeah, what weather it was. In this case, whether it was raining or not. We know the number of overtakes there were. You know, the time that a car went in front of the other car, right? So that's spectacular, right? About the races. We know how often cars didn't finish the race. Okay, so this is one record per race. All right. Now, what is the interesting thing here? We've got also a score for each race. And what is the score? That's basically a group of people that have watched the race, 1,000 or 2,000 people, and that have said, hey, I like this race a lot, or I don't like it a lot. And a 10 is a lot, and 1 is very bad race. It was not exciting, it was boring. Okay. So we've collected that information until, I know, 2019 or 20, and we've got that. So let's have a look at that. I'm just going to open that. Bear with me, we'll get to the link with the machine learning. Okay, so let me first put a little filter here on just 2020. So there we go, 2020. 2020. And now I'm going to show what people thought the score was of each of these races. Well, I'm just showing the race ID. It doesn't really matter. They're all in a location, okay? So, for example, this one has an 8.8, so people really loved it, yeah? And the one after that, it sucked, okay? Nobody liked it. Now, imagine, so this is human beings giving this score, okay? We've got one number per race. Imagine now you want to say, we don't want to collect that data anymore from the human beings, and it takes too long and it's too complicated. We would like an algorithm to tell us how good the race actually is. Okay, how exciting is it? How good was it? Because if you know that, then maybe you can also do something about what makes a race exciting, improve the sport. But okay, that's the reason behind it. But let's say we want to replace that with machine learning. How would we do that, right? So the question then is, we've got all this information on races, right? We had the number of overtaken positions. We have the number of cars that don't finish. We have the weather, and there was a whole bunch of other columns there. But here comes the catch. You can't just throw everything as a machine learning algorithm, okay? Because if you do that, the chance that it starts to come with the wrong answers is pretty big, because it thinks it finds relationships which aren't really there. So there's still this, let's say, this preparation phase, the data preparation and exploration phase necessary for you to at least judge which of those columns make sense and you should be feeding to a machine learning algorithm. So to put it in your context, I want to predict, I don't know, humidity from those sensors. I got temperature and wind speed. Or should I include wind speed or not, right? That's the question in this case. So you want to investigate that first. How do you do that? Well, for example, if I've got, I want to figure out if overtaken positions makes any sense at all to use for, oh, my baby's just walking in. Okay, let's see. I hope he's being nice. Okay, so the overtaken position, has that any influence on the score? You want to find out. So I'll take that. I'll go to score and we'll drag those over. Let me see. I think I need to delete the filter first. Yeah, and I need to drag in the race ID because I want 1 point per race. Okay, so what have we got here? We've got a scatter plot with here the number of overtaken positions. And this is the thing we would like to predict later, right? We want to predict score at some point. So we're kind of just as a human being investigating how much relationship is there between these things. So, I mean, what do you think, right? If you see that, my feeling is there is a relationship here. Maybe it's not crystal clear, but there is some kind of correlation going on, right? So in fact, I could emphasize that point by drawing a trend line here. And it tells me, in general, if you have more overtaken positions, more overtakes, then people appreciate the race more. I can imagine, right? Because it's more spectacular, like there's more stuff happening. If they always stay in the same positions, it's pretty boring, no? So, and this tells me, hey, this means that overtaken positions is probably a pretty good candidate to train a machine learning model on. I want to include that as an input. Does it make sense? So like this, you can do that for all the other data points that you have on the race. Like, for example, I've got the number of cars that didn't finish, like that were in a crash or that had some kind of mechanical failure. You drag that over. And then you can see, hey, yeah, again, here also I see kind of a relationship, maybe not so strong. And maybe it's certainly not enough to make a prediction with just this variable, right? It would be hugely inaccurate because, like, you see they're very far away from these lines. You've got many outliers. But the idea is that if you combine many of these inputs together, then hopefully a model can come up with something that's accurate enough, right? If it finds all of these patterns, it will be accurately predicting the score in this case, or I know the temperature, whatever you want to predict. So, okay, that's a little bit about investigation. Now, training a model, how does that work? I'm just going to quickly show you that. I probably have to, sign in again here as well. Yeah, and I wanted to keep some space for questions, so I'll wrap this up as quickly as I can, Elena. So what's the thing with machine learning? I know you're probably going to use Python and things as well. But there's a certain amount of complexity, right? You need to choose the right algorithm to start with, right? And you need to often tune the algorithm as well in a certain way. And that's pretty complicated. You need to really know what you're doing, even with choosing the right algorithm in the first place. So the nice thing about this is that it hides a lot of that complexity for you. So here I'll show you, we've got a thing called AutoML, where you can basically focus on what you want the outcome to be, instead of saying how it exactly needs to get there. So I've created this procedure here, predict race score. A procedure, sorry, this is the AutoML configuration. So what do you need to provide here is basically, what is the thing that you, what is your output? What do you want to predict later? And what are all the, sorry, this is a bit chaotic. Let me see if I can center this. Yeah, what are all the input data points that I believe could make sense in predicting that? So whether the weather is wet, whether there was a safety car on the track. I think the number of overtakes was also there. Yeah, like here, right? So you just say, what is the input data? What is the output? The score. And then this thing will automatically find out. It will try out different algorithms. It will try out a linear regression. It will try out neural networks. It will try out naive Bayes, all these things with different settings. And then I remember I was talking about the cost function or the cost of something that you can pick the one with the lowest cost, for example, right? Or the one that seems the best. And that you can use then to start making predictions without having to understand all the complexity, right? So even if you're going to do Python, this can be a very nice start, I think, just to play around with the data and to quickly come to some kind of baseline model, and then you can improve it, right? And you can do the hyperparameters yourself. So, so that's it. And let me quickly go to the end result, and then we have a little bit of more time for questions. So when you have the model, you can make the predictions. So I've done that here already for the year 2020. Let me see, where are they? Sorry, just a second. Predicted, I think it's this one. So out of that comes a new little data set for 1 year that makes predictions for all of those races. And let me just visualize that. Let's see how I can do that. Oh, that all looks wrong. I'm going to reconfigure that a bit. Like this, I think. Yeah, that's it. So what are we showing here? Actually, for this year, I also have the actual human opinion about what the score should be, right? What the score is. So that's what you see. I think in blue in this color, okay? That's what the human audience said. Now, what you can do, then you can make a prediction on the same year. You ignore the score that you already had, okay? You make a prediction with all the other input variables. Out of that comes a value, and you can compare how well your model is actually doing. So in this case, that's the orange line, right? What came out of the model. It's kind of a visual way of verifying how accurate it is what you've created. But yeah, there's numerical ways as well of doing that. Okay, I'm going to wrap up really quickly. So that's, I just wanted to show you how you can be very playful with data, how you can quickly use an AutoML, do visualizations, work with geographical data. Yeah, so I hope that serves as some inspiration for you guys in the project.
Yeah, absolutely. Thank you for sharing so many metrics, so many data, so many ideas how to play with it. And we have question from our girls. Is this visualization tool available for everyone or just Oracle?
Oh, it is actually all. It's available, so you can get a free trial in the cloud for a month. You can use it for free for a month. But I think you can also actually download a version. It's called Oracle Analytics Desktop if you want to download it. It's called Oracle Analytics Cloud if you want to run it in the cloud. But that is like a limited time until you need to pay. And yeah, and then you can play with it. It all works the same way as what I've shown. So yeah.
Great, thank you. Any more questions, girls, please? We have like 3 minutes for questions. Let's ask.
Yeah, I should have not taught so much.
No, that's great to see. I mean, we've never seen. I'm not sure about others, but many of us have never seen like these models and this. So you can just. I can't imagine like the amount of work and data that's there. I mean, yeah, it's crazy.
Yeah. By the way, before we do the questions, so I wanted to show you actually, if you want to do these trainings, right, that we do for customers, you can just go there for free. We do them sometimes live, but you can also do them at your own time. Can I quickly show that while you maybe identify a new question?
Sure.
So that's I wanted to show that here. Yeah. So these are some trainings that I've actually built myself. And so those are those trainings around sport that put like machine learning and analytics in the context of the sport. And it makes it a bit fun, right, to do. So the first one is on Formula One, that's Red Bull Racing. The second one is on the sailing that you saw, but it goes into much more detail. And the third one, that's actually, yeah, that goes a lot deeper on data science. I'm not sure how relevant it is for you guys. You've got your training program, right? But just wanted to share it with you anyway.
Yeah, but maybe somebody will be interested in for the future. I mean, for the
exactly.
Thank you. We have a question. What is the best programming language for the machine learning?
Yeah, what is best, right? It depends, I think, on your situation. Python is definitely a big candidate. And the main reason, it's not even the program language itself. It's just the fact how many libraries there are available for machine learning for it. Okay, and I mean there are other candidates as well, but I mean R is still also there. I think in the top languages used, but Python is probably the most popular right now. And popular is good, right? Because that means there's a lot of development in these areas. So that's something that's very good knowledge to have if you're trying to make a choice on what to learn. So yeah.
We have several ideas in the chat about the picture from the first slide that you've been showing, like in the beginning.
We need to, yeah, okay, let's go back to that. I almost forget that. And
yeah,
let's see this one. Yeah, tell me, guys. So what is going on? Is this? Can we wait 1 second? We do it a different way. I wanted to do it like this. Sorry, just a second, Elena.
No.
I'm being very chaotic. I just need to. I need to forward to that question. Sorry, I'm trying to get to that question in my poll. Open poll. Does this work? Yeah. Okay. So now you guys, if all is well in your app, you can say what's going on in the painting.
Really?
Okay, guys. Okay, and I need to share it. Show results. If you still got that open, that would be awesome.
Yeah, we just.
Yeah. Okay. So this is too obvious and too easy. It was indeed created by machine learning, guys. And somebody earned £400,000 with it. So there's loads of opportunity with data, with analytics and machine learning. And there's many cases that nobody's thought about yet. I think you're on the right track with learning about this, because you can apply it to so many things. So I can only wish you good luck with your career on this.
Thank you. If we can take one last question, like Shahnoza, raise your hand, and we can wrap up. Shahnoza, please unmute yourself. Включите микрофон.
Hello, Mr. Kloosterman.
Hi there.
So happy to see you in our webinars. So my question is, now I'm majoring in kind of linguistics. So can linguists work in machine learning field in this sphere? Because once I took part in NLP project, so I became interested to this field.
I didn't hear
I mean,
everything.
in
I
machine
heard
learning.
NLP. I heard.
Can linguists work in this field, in machine learning?
Can who work? Sorry.
Linguists.
Linguists.
Yeah, linguists. In NLP, maybe.
Yeah. So I think. Okay. So there's this. I think there's two parts to any technology, right? So there's the people that use the technology. Like you have a company that wants to analyze, I don't know, texts from what their customers have been saying about them. So they want to use NLP.
Mm-hmm.
And then there's the really high-tech development of NLP algorithms themselves, where I can imagine that linguists are really involved as well, right? To say something about the structure of language, etc. That's probably where linguists fit in there. I would expect. Yeah, but that's like you know, a high-end algorithm actually building algorithms, right? Instead of using the algorithms. That's my initial thoughts about that. I don't know what you think about that.
Thank you. Also, girls asking like about education opportunities for Oracle. I mean, from Oracle on data science, but we can like research it and share with them afterwards. I mean,
yeah.
And if everybody's okay, we can do like a final photo together. Please, if everybody can, those who can turn on the camera. Пожалуйста, включите камеру, мы сделаем фото. Jeroen, are you okay if I will just stop sharing your screen so we can?
Yeah,
like,
go ahead.
Yeah,
you can do that, right? Yeah.
Yeah, I can do
it. Yeah, perfect.
Awesome. So good to see everyone, and thank you for like. We understand that it's just the beginning, but we now have something to build on and move forward with our project. So everybody's smiling. I'm doing a screenshot. You're awesome group of listeners, and Jeroen, thank you once again for being with us today. I will share the presentation and all resources with the girls.
Awesome. No, I thought it was really nice to be here. So I only wish you good luck with your project and after the project. So good luck to everybody.
Thank you. Bye, everyone.
Bye-bye.
Bye.
Bye-bye.
Спасибо переводчику.